So, yeah, like there is no general procedure to come up with an LSH family for a given general metric space. So depending on what metric space is, the way of coming up with an LSH family differs. So now we will see uh, how to construct an LSH family for the Euclidean metric, which is given by r to the power d comma, yeah, the distance function is again Euclidean distance. Okay, so for this we will be using this result, which is a standard exercise in probability. Let x1, x2 and so on xt, or rather, sorry, yeah, let x1, x2 and so on xd be a vector, or let these be normally distributed independent random variables. Let v1, v2 and so on vd be reals. Okay, then the new variable y given as v1 x1 plus v2 x2 plus and so on vd xt will be distributed as again a Gaussian random variable. The mean will be 0 because like all of these have, all of x1 x2 and so on have like mean 0, they are like normal, but the variance will be given by norm v square, where v is a vector given by v1 v2 and so on vd. Okay, so note that all this like v1 v2 and so on vd are constant, so this is like a, so this variable, random variable y, is like a linear combination of the existing IID random variables, where each is sampled from the normal distribution. So we'll be using this for the Euclidean metric, and let's see the proof of this. The proof typically goes through, it goes through the characteristic function. So the hammer which we'll be using is that for given two distributions, if their characteristic function is the same, then it must be the case that the two distributions are also the same. Okay, so recall that the characteristic function is defined as okay, so this is defined as the characteristic function, and it can be shown that for a normal random variable, the characteristic function is given by e power minus sigma square t square by 2. Okay, So now recall that y is v1 x1 plus and so on v dxt. Now the characteristic function of y will be expectation of e power minus it v1 x1 plus v2 x2 plus and so on plus v dxt. And we also know that all x1 x2 and so on xt are independent, so this will turn out to be with the product of j equal to 1 to d expectation of e power it v1 x1 or v1 vj xj, sorry. Okay, we know that xj is a xj is a normal random variable, so it has mean 0 and variance 1. So vj xj will have mean 0 and variance vj square, right? So this will turn out to be using, now we will use this. So this will turn out to be, sorry, vj square t square by 2. Okay, and this will turn out to be minus v1 square plus v2 square plus and so on plus vd square times t square by 2. Okay, so this is the characteristic function, but we already have seen that this is in the same form as the characteristic function of a normal random variable with variance sigma square. So yeah, so this is the characteristic function of y. So y should be distributed as normal random variable with the mean 0 and variance given by norm v square. Okay, so we will be using this lemma to come up with a locality sensitive hashing method for, or a locality sensitive hash family for the Euclidean metric. Okay. So how do we define a hash function in the sense like for Euclidean metric? Fix a, yeah, let's fix a vector v bar then let's define h of p. So for a point p in R bar D, let's define h of p as where t is sampled uniformly randomly from 0 to x, and x is a parameter which we will choose shortly. Okay, so why are we doing this? So ideally, like So the yeah, let's see. So the naive way to come up with a hash function is the following. So yeah, we are given a vector v bar, and like for a given vector p, we just compute like dot product between p and v bar, and we, let's say we call that our hash value of p. Okay, but this is not a very good hash value in hash function, in the sense that it's highly improbable that for two vectors p and q, no matter however close they are, like this is not going to be the case, because like, yeah, these values will be close but they will not exactly be equal. So one way to do this, one way to fix this issue is, like, instead of just taking the dot product, we take the ceiling or floor of the dot product. Now if p and q are close, then there is at least like a good chance that this is going to be true. So we can take this as our hash function. Okay, but we need not like actually stop there. Like, let's say p and q are close, then for some x greater than 1, this is indeed going to be like even closer. Or if x greater than 1, then p and q if p and q are close, then the chance that this is going to hold is going to grow with bigger x. But at the same time, we can't take x to be like as big, like whatever big value we want, because yeah, then like points that are far away also will match in their hash values. Okay, so there will be some optimal value of x, so that we will figure out later. And we will also, so here we also have this extra term like t, which is uniformly randomly sampled from 0 and x. We will also see why that is going to be the case, like why that will help us. Okay, so now what is my hash family going to be? No, sorry. My hash family is going to be the collection of these random variables, the collection of these functions h, where v bar is a normal, or let me put it this way, v bar is a vector sampled from normal of the normal distribution, the d-dimensional normal distribution, multi-normal distribution. Okay, so yeah, if you see for the hypercube case, the hash family, the LSH family that we came up with consisted only d functions, but here it's actually an infinite family of functions, because like v bar can be anything, like it's a this, the support of this is like infinite. Okay, now we want to show that or let's say we want to choose, so there are like a few parameters. The parameter x we need to choose, so we need to choose x such that h is LSH. Okay, that is our goal. Okay, so first let's see, so for that, like we consider like two cases. If p and q are like nearby, if p and q are far, then we want, like if p and q are nearby, we want it to collide. If p and q are far, we don't want it to collide. So fix p comma q comma, we will even fix v bar. We will iterate, or we will, yeah, for now we will fix v bar. Okay, and again we will fix x also. So, and let be defined as eta. Okay, and also define p comma v bar minus q comma v bar as beta. Also, for now, let's also assume that without loss of generality, p comma v bar minus q comma v bar is equal to beta. So p comma v bar is greater than q comma v bar. Then now if we let's have this real line where q comma v bar lies here and p comma v bar lies here. Okay, now fix some p, some v, some q, some v bar, and some let's also the parameter x. So note that in this hash function there are two things that are chosen randomly. V bar is a random vector of normal random variables, and t is a uniformly randomly chosen value from 0 to x, and x is not random. X is a parameter that we'll fix shortly. So here like we are fixing this v bar as well, so only t is random. Then let's see what the probability that these hash values collide. Okay, so the probability of h of p is equal to h of q. So this will occur when does h of p equal to h of q occur? So that will occur when p comma v bar plus t by x is equal to q comma v bar plus t by x. And it's not very hard to see that if beta, which was defined as p dot product v minus q dot product q dot product v, if this quantity is less than x, this quantity is greater than x, then h of p can never be equal to h of q, irrespective of what value t takes. So how do we see this? It's not very hard to see. So h of q or h of p can be written as q comma v plus beta plus t by x, that equal to beta by x plus q comma v plus t by x. Okay, so beta by x is a quantity greater than 1, so this will strictly be greater than q comma v plus t by x. And so is that always true? So let's say this is some 0.9 or something, and this is 1, or in the worst case, like let's say just 1, then the ceiling will be 1, whereas 0.9 ceiling will be 0. Okay, so yeah, this will always be strictly greater than this value, which is nothing but h of q. So h of p is strictly greater than h of q, so h of p can never be equal to h of q. So the only interesting case is when beta is is less than or equal to x. Since we are dealing with ceilings, let's have the real line. So let's say 0 is 1, 0 is here, 1 is here, 2 is here, and so on. I mean, there can be negative integers also, but let's say the dot product between q comma v lies here. Then since divided by x lies here. Now since p comma v divided by x is less than or equal to 1 plus q comma v divided, so this implies that p comma v divided by x is less than or equal to 1 plus q comma v divided by x. We have that p comma v divided by x will lie somewhere over here. It won't cross. So these two blue points, these two cross marks, they will be like within a distance of 1 from each other. Okay, so let's say we can think of this orange thing as a needle. Now if you look at the hash value, so h of p is defined as p comma v divided by x plus, so t by x, but t by x is t is chosen uniformly randomly from x, so we can replace this t by x by mu, where mu is chosen uniformly randomly from 0 and 1. Okay, so now these are the values given for q v by x and p v by x. So now q v by x plus mu and p v by x plus mu, they will lie somewhere like this. Okay, so this point will be q comma v dot product divided by x plus mu, and this point will be p comma v dot product divided by x plus mu. Now what's the guarantee that these two points will lie between two integers, in the sense will lie in an interval which is like a comma a plus 1, where a is a integer. Okay, so that's when these hash values match, right? So yeah, we can see that to be the probability of that will have it will be, so probability of h of p being equal to h of q will be exactly equal to 1 minus beta by x. Recall beta was equal to p comma v minus q comma v, right? That comes from this sliding argument. So we know that, yeah, for now, let's say q comma v by x exactly coincides with 1. We know that p comma v by x lies somewhere over here. Then this orange needle, it will be shifted because of mu, it will be shifted for some random value between 0 and 1 in the rightward direction. So that shift, so let's say it shifts here, then the ceiling values of these two are not going to be the same. So that happens only when this mu lies in this range. The probability of that mu doesn't lie in this range, but let's say this length is L, then mu should lie between 0 and L. That is when the needle lies between 1 and 2, and that length L can be seen to be 1 minus PV minus QV by X, and PV minus QV was defined to be beta. Okay, so that's how we get this. Okay, so all right, so fixing V, we get that this is the probability that both the hash values match, but V is not fixed, V is also random. So now what can we do? Well, we just okay, let's see. So now probability of h of p is equal to h of q will be equal to 0 to beta probability that is equal to, let's say, so is equal to beta. Yeah, when this happens, we have seen that with this probability they both match. So this is the probability, and yeah, as we already seen in one of the above lemmas, for fixed P and Q, PV minus QV can be written as P minus Q times dot product with V. So for fixed P and Q, and where V is a vector of independently chosen normal random variables, so this itself will be distributed according to normal distribution with mean 0, or Gaussian distribution with mean 0 and variance non P minus Q whole square. Okay, so we just substitute that thing. So let's say eta is equal to non P minus Q, then this probability we can rewrite as, so probability of, okay, so we want P comma V minus Q comma V is equal to beta, so that will be probability of P minus Q comma V is equal to beta, or Q minus P comma V is equal to beta. So this will be equal to 2 times probability of P minus Q comma V is equal to beta, and okay, so probability, like working with probabilities itself is like not correct. This is basically the marginal distribution, so that will be, so I'm vaguely writing this to be not, this is, so basically, this is like not very correct, not very accurate. Like what we want is the PDF of eta square at beta. So that is going to be or 2 times eta square. So this is going to be PDF of this at beta, but we want like 2 times the PDF of n of 0 comma eta square at beta. So this is going to be 2 by root 2 pi n eta exponential of minus beta square by 2 eta square. Okay, so we substitute this here and obtain that probability of h of p is equal to h of q is equal to 2 by root 2 pi n times exponential of minus beta times 1 minus beta by x dx. And the limits, so beta, yeah, this is like where, sorry, d beta. So beta can vary from 0 to infinity, but we have already seen that if beta is greater than x, then this probability is going to be 0. So this just varies from 0 to x. Okay, now we want to choose x such that so remember that like in locality, sorry, APQ queries, the query time is going to be something like rho tilde of n power ln 1 by alpha by ln 1 by beta, where alpha is an upper bound on the probability of given distance between P and Q is less than or equal to R, and beta is a lower bound on the probability, alpha is the lower bound on the probability, whereas beta is an upper bound on the probability that h of P is equal to h of Q given they are far away. And and what we are trying to distinguish is in between R and R times 1 plus epsilon. Sorry, this should be greater than or equal to okay. So we have to choose x. So here we can see that so here we can see that so eta was chosen to be the distance between P and Q. So we want to differentiate between eta and eta times 1 plus epsilon. So if we define this integral as if we define this integral as P of eta comma x is the parameter, then we want to choose x such that 1 by P of eta comma x by ln of 1 by P of eta times 1 plus epsilon comma x is minimized. So we want to choose the parameter x such that this quantity is minimized. So that's when the query time will be minimized. Okay. So but it turns out that this integral itself is a very notorious integral. It's not like very easy to compute, and also this thing is also not very easy to compute. So this work, so this scheme of LSH for Euclidean metric was given by these authors, Datar, Imorlica, Indic and Mirokni in 2004. So they gave this scheme of locality sensitive hashing for Euclidean metric. So what they did was they confined to some computations and showed that they using computations they show that it is possible to choose the parameter x such that, so this ratio ln 1 by p of eta comma x by ln 1 by p of eta times 1 plus epsilon comma x is going to be at most 1 by 1 plus epsilon for all, for any eta, basically for any eta greater than 0. Okay, so yeah, that's what they could show. So this gives us a locality sensitive hashing scheme, and for Euclidean metric space, and using this locality sensitive hashing we can solve APQ in Euclidean metric where query time, again it will be of the order O tilde of d times n power 1 by 1 plus epsilon, and pre-processing space will be O tilde of d times n times 1 plus 1 by 1 plus epsilon. Okay. Yeah, so that ends the lecture on like approximate nearest neighbor using locality sensitive hashing.